throw this in your pocket, pick up a belt.
Yeah, let me.
Works.
Thanks. Oh, good. There's huge chalk.
You like that?
But it's colored. Is there huge white chalk?
They used to have even huger chalk.
Yeah.
Remember that?
Yeah, like. It's okay.
Did you need something, Eva?
No, I was just wondering if there's huge white chalk, but there is not. That's okay. No worries. There's no clock here, so it's hard to say. But
So this screen becomes a clock?
yeah, that's
So
I
just
was
do a
told. Yeah,
screensaver?
thank you.
I asked him if we knew how to just make it go to that, but apparently we don't.
No, that's okay.
There is an old-fashioned analog clock. I don't know where it is.
Oh, don't worry.
it's
I have a phone. I have a phone.
Okay.
That's okay. I'll.
Okay, so Eva Silverstein will be giving her first lecture on inflationary cosmology and string theory and so on.
Thanks, Joe. So it's a pleasure to be here as always. So this week you'll have two series of lectures on cosmology, broadly construed, and I think that's healthy because you'll sort of see it from all sides. And that I'm referring to these lectures and those of Leonardo Senatore. So since I'm going first, I'm going to start with my first lecture as a fairly quick but hopefully reasonably complete introduction to inflation, including, I'll emphasize a range of dynamics that can come into the process, both theoretically and in a way that the data is sensitive to. I'll try and introduce also the density perturbations, which are the phenomena that lead to observable consequences most directly. And then I will attempt, if I get there, to just flash for you the current status of CMB data. And this is, I think, the right starting point for these lectures. One of the things we'll see in studying inflation is what we call its ultraviolet sensitivity. So as we'll see, based on simple notions, basic notions of effective field theory that you've also been studying for other reasons in this school, we'll see that any model of inflation makes assumptions about Planck-suppressed higher dimension operators. And in the simplest cases, makes assumptions about an infinite sequence of those. So this is a subject where I'll put it in the dark nonetheless, but the use of string theory is highly motivated because it is a theory of, at least a good candidate for a theory of quantum gravity, which if you think about the subject carefully, it really is required. So it's a chance to do some real science with string theory, but it's also just an interesting subject in itself, the early universe cosmology. I will focus on inflation for reasons that I'll get to, although it's interesting to think about possible alternatives. But time being finite, I won't dwell on that. Okay, so let me start with the basic motivations. Very briefly in pictures, macroscopic motivations that led Alan Guth and others to consider the possibility of inflation, which, as I imagine you all know, is a phase of the early universe which let's just fix to a flat slicing of space, thinking homogeneously at first, is driven in a way that leads to a scale factor A of t in this metric that grows exponentially, or at least accelerates, as a function of FRW time t. So let me just briefly review for you the basic motivations that led the early pioneers to this idea. Well, one thing you can say about it is that it's the generic long-distance physics. This behavior is driven by potential energy, which is the the most relevant, includes the most relevant terms in the Lagrangian. But more dynamically, here was the picture that people were faced with. So the universe is expanding. I'm going to draw a cartoon of that in a way where I don't allow for accelerated expansion. So this is time t, and let's just sketch a couple of time slices of interest. So one of them is now, where the energy density is basically 10 to the minus 4 eV. Another important time scale is recombination. So if you think of this in terms of a redshift factor by which the universe has expanded, this is roughly at such a factor of 1,000 relative to today. And the density is 0.3 eV to the fourth. Do you guys know why it's 0.3 and not the scale of atomic physics? So recombination is when atoms first formed. Any questions about why it's this and not eV? Yeah, okay. It's because there's way more photons than baryons in the universe at that time, and so the photons dissociate the atoms, and it takes longer for the atoms to form. So the subject of your early universe cosmology is beautifully sensitive to all sorts of things like that. And I won't be able to cover them all by any stretch, but it's a great subject to learn for all sorts of reasons. Okay, but what Alan Guth and company did was to ask what happens if you extrapolate this picture back to some high energy scale. For example, the Planck density. Excuse my writing. Or the gut scale, or whatever you like, among the high scales that one imagines in nature. And you ask the following question. So it's known that the microwave background radiation that is detected on Earth with telescopes is approximately 3 degrees Kelvin plus order 10 to the minus 5 fluctuations that we'll be very interested in. And you see that these fluctuations are inhomogeneous, whereas the leading thing here is very, very homogeneous in contrast. So that is to say, if you look at the sky from all directions, the temperature, the effective energy that you see in this radiation that comes to us, looks to exquisite precision, it looks the same from all sides. Okay, so if I kind of sketch that in this picture, this is us looking back. And if you draw this picture correctly and trace light rays back, you find that the source of the radiation from diametrically opposite sides of the universe comes from these directions that I've sketched here. And if you just have a naive picture of the expansion extrapolated back, not allowing for early acceleration, you can get puzzled by why the temperature is so similar in these directions, given that the source of it was never in causal contact. Okay, so this was called the horizon problem. Another problem based on sort of theoretical ideas was if you take grand unified theories seriously, you'd imagine things like monopoles around in the universe unless you make special assumptions, and curvature of space and so on, and none of these things are seen. The solution at this macroscopic level is simply to relax that assumption that you should extrapolate things back in this naive way. And if instead at the same cartoon level of drawing I can hopefully show you that if you allow for early acceleration, you avoid this conclusion. Okay, so the equations of general relativity on a simple FRW background like this one that I've written here take the form, as I imagine you know, or the one that's most relevant here takes this form. And so if the right-hand side is approximately constant, then you can see that you get this exponentially growing dynamics. And otherwise you get some approximation to that, which we will also be interested in. Okay, so this was the macroscopic idea behind it originally. But one does need to exit from such an inflationary phase into regular cosmology with a decelerating expansion. And so let me remind you of the more general homogeneous dynamics of FRW cosmology. So we can talk about what is required minimally to model that. So I'm writing here the Friedmann equations, which are the Einstein equations with homogeneous stress energy sources. So we can focus on this one because with conserved stress energy, the other one comes out automatically. And one thing we see, as I just said, is that we definitely need to model this some source of changing energy density on the right-hand side, because even though we want it to be approximately constant to begin with, to get this, it needs to exit from that phase. So for exit into normal decelerating FRW. Okay, so I think it's fair to say that the simplest way to model that leads you to making the source here, rho, dynamical, so it needs to be dynamical, by obtaining it as the energy density of some scalar field. So in particular, so this rho in general will include, if we add a scalar field to our model, it'll include the potential energy as well as kinetic energy, and all sorts of other contributions that we'll be quite interested in these lectures. But basically, for the same reason we reviewed over there, it's sufficient to get inflation to have this potential energy be nearly constant early on and then exit. So there are many ways that can happen. The model-independent way of saying all this actually is that we will need the time variation of what I called H here, Hubble, which is, as I wrote, A dot over A. Stop me again if you have any questions, because I think it's almost certainly largely familiar to you. But anyway, so to get this phase of early acceleration, and as we'll see in more detail shortly, to get it to last long enough to do this job of diluting additional degrees of freedom that could have been around. In fact, why don't I just say that now? So currently we have this tiny energy scale in physics in the universe in terms of the average energy density, and the ratio of the two is, for example, if you imagine a scenario at the gut scale, you find that in order to dilute all that stuff at the gut scale, you need so-called 60 e-foldings of inflation. And in order for that to be true, not only do you need H to be approximately constant, you know how long that needs to hold at minimum. And basically, its normalized derivative need to be about the percent level. Okay, so that's the model-independent way of saying what it is that one needs. So perhaps I should have said that, in fact, first. Now I'm modeling that combined with the need to exit by introducing a whole nother field into nature. So it's a big step that these guys took, but for good reason. And so one can have this physics of a nearly constant v early and then exit from that phase where it drives the expansion. Okay, so, and there are many ways that can happen, which we'll describe. And as we'll discuss in detail, the field is generally a function of space and time. We will start, as I've been saying, by studying its homogeneous evolution and then incorporate its fluctuations, which are functions both of time and space. And one can study this usefully in various different gauges in general relativity, so we'll also be concerned with that. But for now, let me start by discussing more about the homogeneous part of the story. Are there any questions? Any at all? Tom?
So these are all very funny numbers, but
Yeah.
these are numbers that you are given that have to come out at 6-fold that you got over.
I agree, and we'll talk a lot about that. Yeah, it's so the 60 is of course a lower bound for this idea. I should also say though that you could take a completely opposite view, a very empirical view, and say, which I haven't gotten to, but the CMB only actually gives you direct access to about 10 e-foldings. So you could take the view that that's all you really know for certain, and the rest of it is terribly speculative. But it seems to most researchers, I think, to be kind of ugly to try and introduce extra structure that would correspond to that. So the 60 foldings seems like the simplest interpretation of all these facts put together. But yeah, thanks for the question. Any other? Also, like as Nadi said, tell me if you want me to speed up. Yes? Okay. I think you got more shaking heads. I think, okay. I don't know. I mean in a good way, like. Okay, so I really want to be careful with, one of the goals of these lectures is to, and Leonardo's also, which will be more from the so-called bottom up, will be to be more systematic than the sort of dumbest thing you might write down, even though I should say the dumbest thing you might write down is quite consistent with the data. So actually, that's not true. Actually, the data has excluded the dumbest thing you might write down, and we'll get to that. I'll get to that in this lecture. The cosmologists have discovered a new parameter in nature for reasons that I'll explain shortly. But it's almost the second dumbest thing you would write down. It still works. Okay, so in order to get there, let me just sort of. Okay, so we've been motivated to introduce the scalar field for macroscopic reasons, and one of the things that's going to happen, and we'll keep going with that for a while, but one of the things that will be very, very interesting are the quantum mechanical fluctuations of the perturbations, and that's the thing that, of course, leads to the observables in the microwave background. So having introduced the scalar for macroscopic reasons, you get an output that's just phenomenal, that gives detailed information about things that are then observed in a way that wasn't anticipated at the time. So this, we've made a huge step here. We've added a whole scalar field in nature. Of course, this is a formal school. In string theory, we've added way more than that, of course. But anyway, we'll see how some of these things fit together. Okay, so let's go with that. Let's consider this scalar field sector. So we'll have an action that, of course, includes gravity. but also we'll focus on the scalar field dynamics coupled to that. And, if I just write a semi-general Lagrangian, it would look like this. It could depend in many ways on the field, its derivatives, and on other degrees of freedom that might be around that couple to inflation in one way or another. And the whole thing is quite sensitive to such possibilities. So let's keep that in mind. Now I'm going to discuss briefly two extreme possibilities of examples of this much more general thing. One of them has an acronym, let's say, of single field slow roll inflation. So this is slow roll. It's kind of a misnomer because the inflaton rolls slowly in many mechanisms that aren't in this class, but never mind. The definition of this is simply that the inflaton dynamics is well approximated by a simple potential term plus an ordinary two-derivative kinetic term. Now, let me give you another extreme, which is interesting partly because it showed originally how broad inflation can be. And it also came out of string theory, something that people hadn't quite realized just from effective field theory, although in the end they took that and, as you'll see from Leonardo, took it as inspiration and other things for inspiration to write a more systematic treatment of this stuff, including the perturbations from the bottom up. But it's a funny thing about theoretical physics is sometimes we work by example first, and that's what happened in this context. So anyway, this is just a semi-random example, but it's an interesting one, which teaches us some fun things about scalar field dynamics and can be applied as well to inflationary cosmology. So I'll just write it down as a kind of interesting counterpoint. Sorry, there's of course also the Einstein term, as always. And of course, these are just two of many possibilities. So this one is probably, well, they're both pretty familiar in the community, but this one is probably the basic one that you know. And I'll.
Could you maybe raise that?
Yeah.
Or so, just so they can see it in the back.
Okay, sure. It actually stands for what you probably think. It's Dirac-Born infall. This is, I'll show you in a second. This is, so it might look reminiscent to you of the Born-Infeld action that describes propagation of relativistic particles. You know, if you have a relativistic particle, you can describe it by a similar action, and this action gives you the ordinary equations of relativity. What that thing over there is the same thing for a D-brane moving in anti-de Sitter space. So if you take the famous ADS-CFT, the version that Juan first talked about involving the n=4 super Yang-Mills theory, this is the dynamics on the Coulomb branch. So the first term of this describes the the motion on the Coulomb branch, which, as usual with ADS-CFT, we get best in this in the large radius limit from the gravity side. So if you take a D3 brane of string theory and you stick it at a radial position So basically, if you're used to, let me just write the metric of ADS5 and in a Poincare slicing. Basically, up to some normalization, the field phi that I described there is proportional to the radial position of this D3 brane in ADS CFT, where the radial coordinate is defined as here. So this comes from the effective action on D branes, the Dirac-Born-Infeld action, evaluated in this geometry. And what's happening is it's a very, if we focus on the homogeneous dynamics, you can see that the speed of light, so basically this is analogous to, x dot squared in the dynamics of a particle moving on a line x. And just as there, where x, the velocity is less than 1, and the dynamics from the Born-Infeld action, it enforces that. Same is true here. So without solving any equations, although of course we did to make sure, the dynamics just always enforces this condition. So I might as well just finish. I'm glad you asked the question, because it gives me a chance to just sort of finish this contrast between these two types of scenarios. So what this does is it enforces through these non-trivial interactions in the scalar field sector that whatever the potential energy is, say we think about this phi as a candidate inflaton with a potential, it as it rolls toward phi equals 0. Okay, let me draw this in a more exaggerated way. As it rolls toward phi equals 0, it's forced to satisfy that phi dot squared is less than phi to the 4th over lambda. Okay, lambda is the usual 't Hooft coupling of ADS CFT. R to the 4th is like lambda or something. So at large radius, this is a very powerful effect. And it turns out that because of this, it doesn't matter what the potential is, the field can't go faster than this. And that turns out to be a viable mechanism for inflation, which requires that the potential be nearly constant. The traditional way to make the potential nearly constant is the thing that works in the top case, the single field slow roll. These things can all be generalized to multiple fields. But in the single field slow roll, instead of interactions that slow the field down per se, instead one postulates a nearly flat potential. And that also, so you get pictures like this. And that also suffices to give inflation. And I'll talk in these lectures a lot more about this case and its UV completion as opposed to this case, although they're both interesting. And this I'm introducing now just to give you, as I said, a clear understanding of the range of dynamics. Yeah?
Why do you apply it for slow
No. Okay, good. I went too quickly. Thanks for asking. These are two different cases, very different mechanisms for inflation. This one works on a steep potential, so it can be steep. So that was one extreme case. The other extreme case is that you get inflation because you have a a potential that is so flat that the field barely rolls down. And I'll get to the equations describing exactly how much that needs to be true. You still look confused. I must be. Can you try and ask your question again? So here, we take this, we kludge in a potential, and I haven't gone through the full solution of the equations of motion, even classically here, although it's it's very explicitly done in the papers. But I'm just telling you, and I hope it's intuitive, that this piece will just not allow any violation of this condition, and that's true regardless of what V is. Yeah. So these were just two very different cases. Was the point? It turns out that they are fully distinguishable using CMB data. Because this involves interactions, it leads to detectable so-called non-Gaussianity. I haven't really gotten to that yet, but just to anticipate Gaussianity in the primordial perturbations, because basically it's a direct result of the interactions that it involves. So, are there any other questions? Yeah.
The first one is sort of is an obvious way in the picture drawn that you can get an exit, like it leaves flat. The other second one it looks like it's zero.
Well, in fact, in the first one, I'm glad you asked that as well, because I drew it like this there are now many reasons to draw it like this. One reason that was in my head when I drew it like this at first was just this was sort of the classic picture of new inflation introduced by Linde and Steinhardt and Albrecht and Steinhardt. There's another much simpler possibility, which would just be literally a parabola. So V of phi equals 1/2 m squared phi squared. That also has an exit from inflation because, as we'll see, it gives slow roll inflation way out on the potential. So, for phi bigger than the Planck scale as a dimensionful quantity, a four-dimensional scalar field has dimensions of mass, and for phi bigger than m Planck sufficiently, you get slow roll inflation, and conversely, when the field gets down to where that's no longer true, it exits. So this example has, in fact, the minimal number of parameters needed to describe the whole thing. This has more structure in it. And actually what I was saying a few minutes ago was that very, very recently, putting all the current CMB data together, this possibility has now been quite strongly disfavored. And so it's actually in that sense that I'm saying that the cosmologists have discovered a new parameter, because you need more than this. Yeah. Okay.
In what sense is it less parameters than others?
Yeah. Or zero. I know. I agree. I always ask. No, I like the question. I always bother people with this myself. But what I'm saying is, this is. I'm viewing this as the origin in parameter space, and you can always ask that. You can just say, the question is, what is the correct notion of the origin in parameter space? Yes, thank you. Right. Yeah, I actually have the same sort of philosophical question about how one thinks about adding parameters in data analysis, but one thing that what I can say is, relative to this model, you've discovered another parameter, and we'll see in a little bit later why that makes a lot of sense from the point of view of any UV completion and string theory in particular, for reasons that are similar to your phi heavy, phi light model. So I'm going to get there shortly. So yeah. Okay, so I think I said what I really needed to say about this sort of these extreme ends. I now want to lay out the case of single field slow roll in more detail, just so we have everything down. Okay, so if you take the Lagrangian, this one, and you vary it with respect to the field and get the equation of motion. In this case, you have the stuff that you would have without inflation plus the Hubble friction term. So that comes from the a cubed in the determinant. People haven't seen this before. So let's unpack this a little bit more to determine what we need for inflation in this simple context. So, well, the first thing we said before is that we want the potential energy to be much bigger than the kinetic energy. Well, what we really showed was we need some constant source of stress energy, but this would suffice. And if you take ordinary kinetic energy, it dilutes much faster than potential energy does. So let's first insist on that. So what does that mean? Well, so that means phi dot squared over the potential energy. Now, from the Friedmann equation, the potential energy is of order h squared and Planck squared. So it's useful to just go back and forth between those two. And okay, let's call this epsilon, and we know we need it to be small. Okay, so far so good. So again, I just use from here v equals 3h squared and Planck squared. Okay, so but we really need that to last for a long time. Actually, before we even get there, let's well, okay, yeah, we want this to last for those 60 e-foldings I suggested before. So basically, we want the system not to change rapidly. So let's look for a regime where in that equation of motion we can neglect the phi double dot term in favor of the other two terms. Okay, so first off from that we get that phi dot goes like v prime over 3h, and so epsilon could equally well be written in terms of the derivative of the potential normalized in this way, the first derivative. The second thing we need, though, is was it self-consistent to get rid of the phi double dot? So for consistency, so for this, we need that term is small compared to the two that we're keeping. Okay, and you can work out by plugging into the solution and taking the derivatives that implies that, well, this combination turns out to be this. So in other words, we already said epsilon needed to be small, and so we also need that what is usually referred to as eta sub v, or the potential energy form of the second slow roll parameter, that also needs to be small. Okay. So these are the famous slow roll conditions. Let me quickly show you how they work out in the case of the m squared phi squared model, which I like to think of as the origin of parameter space. Yeah.
However, all of that is under the assumption that initially phi dot was 0, right? I mean, the initial value of phi dot is completely independent. It's just another parameter.
Well, certainly, you could ask how this process starts and what are the, what special choices may or may not be needed in order to begin the process with this being true. So indeed phi dot squared over v needs to be small by not a huge factor, just needs to be a control factor of order 5 or something, 1/5 or something, to get inflationary dynamics to take over. So what happens is, even if you start with some phi dot, it dilutes very rapidly. So I don't have time to cover everything here, but if you analyze the homogeneous evolution in kinetic energy dominated scalar field theory, that rho dilutes like 1 over a of t to the 6th power. So it dies rapidly because of the exponential expansion. So what you really need to get inflation started is a modest assumption about such ratios in the beginning.
Sorry, I'm confused. I mean, okay, so it dies rapidly, sure, if you achieve the exponential expansion, right? But in order to achieve the exponential expansion, you require it to be small. Right? I mean,
so we're requiring it to be small. So I'm agreeing with that. We can start out with it being less small than it has to be for phenomenology. So yeah, I'm agreeing you have to require it to be somewhat small. But what I'm saying is, it will continue to dilute relative to the.
Yeah, sure. Okay. It dilutes rapidly. Yeah, okay. But then you can say that means that near the origin in A, it's actually dominant, right? I mean, like
near the origin in A, absolutely,
okay.
Absolutely.
Right.
But that's but we're interested more in the late time physics.
Sure. So, okay. But for the dilution to take place in the exponential manner, you require it to be small so that the regime can be onset, right? So that
yes. Yeah. That's this condition, absolutely.
Oh, okay. No, I mean, yeah. Okay, maybe I'm confusing myself, but.
No, I mean you're quite right about the mathematics. People get very philosophical about what can be said about the measure on initial conditions, et cetera, and that's where I thought you were coming from. But absolutely, mathematically, you need some hierarchy, but once you have that, you have this dilution of the extraneous stuff. Yeah. There are. It's kind of ironic, but we have a better handle on the earlier stuff than we do on that kind of intermediate reheating phase, although certain basic things need to be true, such as reheating into ordinary particles and not too much into other stuff. So there are constraints on it, but those constraints are not too hard to satisfy if you just play around with mechanisms. I think it's an interesting growth industry, actually, to study more about reheating, and it's just hard to get an observational handle on very directly. So yeah, and we could discuss that in more detail as you wish, but I think that's the short answer. Okay, so let me just spell this out for m squared phi squared, and I mean, again, I completely agree with Nati's question that really there's an infinite number of parameters in cosmology. Just some of them are set to some arbitrary 0, but I think we know what we have in mind. So let's talk about this model very quickly because it's very simple. Okay, so that's our V, which means that H is m phi over m Planck. And in the regime of slow roll, which we will check for self-consistently, we need, this is V prime. This is the 3h phi dot term from that equation of motion. Plug in h. So again, I'm using here that's h squared m Planck squared is v. Okay, so you can easily see that putting all these things together, if you form this ratio and require it to be smaller than 1, it's saying that phi relative to the origin of this parabola needs to be bigger than m Planck. Okay, and in the real world, putting in all the phenomenology, it turns out to be, this number turns out to be about 15. But we'll see this wasn't an accident, that, speaking a bit loosely, but we'll see a more concrete version shortly, this relation between, let me get there. But it is a true fact that, in some sense, some of the simplest possibilities for inflation have this feature that the field ranges over a large number of Planck units. And that's the case that is particularly sensitive to quantum gravity, which is one of the things that I want to get to. In fact, right now. So we're doing okay on time. Okay, so far is this all good so far? Any more questions? Okay, so so the last thing I want to say about the homogeneous case, I think, is so still sticking with that. I want to bring in Wilsonian effective field theory, meaning we don't just write down that action. We write down what I wrote before, but we try and include less assumptions, and so we add in an entire sequence of operators of dimension delta, expanding around this nice simple perturbative theory, with mass scales making up the difference, and the UV sensitivity that I alluded to earlier can be seen immediately from what we said. So an example of an operator like this would be to take whatever potential we were talking about and form the following dimension 6 operator, and even let it be suppressed by a mass scale m star that's up at the Planck scale. So let this term be as small as it possibly can be, given the scales that we know of in nature, or that we think we know of in nature. So in that sense, this is a conservative statement. Well, what does this do to epsilon and eta? So, any takers? What is the order of magnitude of the change in eta that this produces? Order 1, right. Whereas it had to be, for inflation, it needed to be of order a percent. So it's in that sense that any model of inflation is making assumptions about these terms. Okay. Well, yeah, that's right. We'll get there. In fact, that was the next thing, so thank you. I can see I might not have been totally clear. Here I was doing m squared phi squared. I stopped doing m squared phi squared, and now I'm doing something a bit more general. Still in slow roll, just to be specific, but not assuming that particular model. So you could imagine an inflationary scenario which didn't go over a super Planckian range in phi. And even for those models, this is true. So there's this minimal level of UV sensitivity in the whole subject, never mind what form of inflation it is. That doesn't mean you can turn it around and determine the theory of quantum gravity from this. Clearly not. We have some hopes of certain distinctive signatures and so on, but that this doesn't imply being able to invert the problem. But it's just true, again, that any model of inflation has made assumptions about these terms.
Also,
Sorry.
vector field theory is a derivative expansion. That's not a field power expansion. So large values of the field don't necessarily quantum gravity.
Well,
Assuming you can get base.
so I think what you're saying is that the energy scales remain low, or somewhat lower than the Planck scale. So let's get to these things. I'm glad you're asking all the right questions. Okay, and actually, let me make. I'm like as with Nati's disclaimer in his lectures. I'm being terrible about references. There are books. There are many books and reviews of this subject in which you can find them. But one thing I want to call out is this KKLMMT paper from I think 2003. It's a kind of specific scenario for small field inflation. But to me the main import of this work was that it got people started being really careful about this point, rather than just considering random possibilities even from the top down without properly treating this problem among other problems that we'll get to. So okay, so that, and then I'm going to focus in these lectures. I'll sort of give a laundry list of various mechanisms people have talked about, including that one, but I'll focus on a different class in these lectures, which I think are more promising, but we don't really know. Again, I highly recommend that paper for its careful treatment of this issue. Okay, so well, it's already been said. What we'll find when we study the perturbations, which I have not introduced yet, is that this corresponds also to a detectable level of primordial gravitational waves. So it's a case that's very much worth understanding. And as was said, it's formally infinitely UV sensitive. So the so-called large field inflation, in a sense is infinitely UV sensitive because one does need to keep track of an infinite sequence of these higher dimension operators. Another less incendiary way to say that is that it's at least sensitive to the symmetry structure. So which, by the way, from a low energy field theory point of view, the symmetry is enough to protect some of these classic models from corrections of the kind that I discussed over there that would come otherwise perhaps from, say, quantum effects. One needs to understand this already, though, at the level of at tree level. So I'm saying a few things at once in response to the questions, which I like, so I want to make sure to say everything. One true fact is that this example gives inflation classically in the way that I said. It's also completely radiatively stable. If you take this theory just coupled to gravity and you compute loop corrections, it's the potential being the leading thing in the effective theory that breaks what otherwise would be an exact shift symmetry of the field phi to phi plus constant, is enough to protect the inflationary model from important corrections. This is actually first done, as far as I know, in a paper by Lee Smolin, which I like to refer to because it's an opportunity to do that. No, I'm really sincere. I think the first correction he finds is something of this order, which is below where it matters. But any thinking person would be curious as to whether, given this infinite sensitivity, as to whether the theory of quantum gravity that ultimately pertains in nature would have such a strong symmetry. And we'll ask and answer that question in string theory later, but that's indeed one of the motivations. So did I cover the questions that were asked, or is there more? Okay. Now, one thing I want to do is, and I can actually build on this simple business of integrating stuff out classically, is, staying homogeneous for a little bit longer. I want to now cover some basic effects on inflation that can come in from additional degrees of freedom, and that could couple to the inflaton phi. And of course, this is a huge subject, but there are very simple lessons that I want to share with you about, which I think are pretty basic. So actually, let me start with the following. This is actually similar again to Nati's story that he began with. And for me also, it will be a toy model, but one that reflects the basic physics that came out in this sort of inflation and string theory. So let me consider the following system where we'll have a light field and a heavy field and couple them in this way. So so in this action, or this potential, the heavy field wants to sit at this value phi naught. If it did, and let's say this mass is big, we'll find that we're happy with this mass being bigger than the ultimate Hubble scale of this system when we take this phi L to be our candidate inflaton. So what I'm talking about here was worked out in a paper of Shidong et al. In 2010. Okay, so so if this heavy field were just really rigidly stabilized at this value phi 0, then you would just plug it in here and you would get an m squared phi squared model for phi left, or excuse me, for phi light. Okay, but that's not what you get if you actually classically integrate it out properly, which is a trivial thing to do, solving for dv d phi heavy equals 0. Okay, so we can all do that. And what you find is that instead, of course, the two terms share the energy cost, the potential energy cost, in a way in which they play off each other. So, the absurdly naive thing would have been that, again, phi heavy sits at phi naught and gives an m squared phi squared. Instead, what happens is that, as you can see, this potential actually exactly flattens out at large field values. And all that's going on is very trivial, but all that's going on is, again, that potential energy is building up. And this term, the heavy degree of freedom, can adjust. And it adjusts in an energetically favorable way. And that leads to this flatter form of the potential. And if you go through this and look at the numbers and so on, you'll see that this is something that does not involve, light fields. The scale of interest in this problem is, the Hubble scale, and instead of being light by that criterion, this applies to very heavy fields. So this is a sort of specific way in which any high energy degrees of freedom, high mass fields, for example, that's coupled to the putative inflaton can affect its dynamics. And mathematically, this is completely trivial. This is just obviously classical dynamics. By the way, unlike in Nadi's lecture, I need to treat the kinetic terms, and I ignored them here. But in this paper, you can see a description of why the kinetic terms don't change this conclusion. Okay, so if you imagine that the ultraviolet completion of gravity has heavy fields in it, and you allow them to couple to the inflaton, then I claim you would not expect m squared phi squared. You would expect something flatter than that. And in fact, this is a kind of post facto explanation of such an effect that happened in a certain string theory mechanism where one found a funny shape for the potential, plus some other interesting structure of this kind of monomial form that one has for m squared phi squared, but where it was just coming out that p, this power p here, for reasons that I haven't explained to you, but I'll get to, was coming out just less than 2, generally. For example, 2/3 or 1 or various other values that have been studied. And so, in other words, in string theory, the closest approximation that it has given to the m squared phi squared model or large field inflation generally, this is the pattern, and it really can be understood in this kind of trivial way, that it, as we'll see, it'll come from an action that's perfectly analytic in the fields, but which, when you integrate out heavy degrees of freedom, it reduces the low energy theory to this pattern. And these in fact are viable only because of this. They remain viable in the data only because of this, for lack of a better term, so-called flattening effect. And this, again, is relatively new. This is as of the January 2015 Planck release, including their collaboration with the Bicep Keck team. Okay, so that doesn't mean anything about whether string theory is right or these models are right, but it's encouraging, and I think it makes perfect sense. So this parameter, which relative to m squared phi squared the cosmologists have discovered, I'm saying is just quite to be expected from a slightly more high energy point of view. Okay, so another thing that can come in, which in terms of couplings of other fields, is here I emphasize heavy fields coupling to the inflaton. There can also be fields that couple to the inflaton and as a result of that become light at various points in the process. So let's think about that as well. As long as we're trying to be a bit more, somewhat systematic, let's think about that. So let's say temporarily light fields due to the coupling to the inflaton. So, for example, if you consider a term in the Lagrangian which has various places where some extra sectors, let's call them chi, couple to our putative inflaton phi, you can ask, well, what does that do? one thing it does is it renormalizes the effective action. And in fact, that DVI model I mentioned is the extreme strong TIF coupling limit of a supersymmetric version of this, which gave those important corrections to the kinetic structure of the theory. But now let's work instead in the opposite regime where lambda is small. So not in that type of regime I mentioned earlier. This and that are kind of on opposite ends of a spectrum of possibilities. Okay, so what happens here is, depending on just how small this mu that I've written is, as phi changes and starts to hit these values phi sub I in this expression, the mass of chi is varying. So it's a time-dependent. So we have a time-dependent mass for the chi field as a result of the fact that we have this rolling phi field that we have in mind, say during inflation. So really, I should say, or it's useful to think about this in terms of the frequency of, say, momentum modes of the chi fields, which have this basic form. Classically in this example. Now what we'll do for this purpose is consider the physics well within the time scale given by the inverse of Hubble. Okay, so there is this k. So this k over a is the physical momentum in this expanding background. So remember, just to make sure this is clear, we have this metric, and the k that I've written, I think this is called co-moving, is the Fourier transform in this x-coordinate. On top of that, there's the fact that the space is expanding, so the physical momentum is k over a. Is that clear? Okay. So this is a general time dependence of such a field. However, if we consider the dynamics well within, so for time scales short compared to the Hubble time scale, the A of t is approximately constant. So it's useful to just consider the field theory problem of a field coupling to extra degrees of freedom first, and then it can be included in inflation as well. Okay, or in the expanding universe. Yeah. Uh-huh. L. This is meant to be an additional term in the Lagrange of the inflaton phi. I'm going to try and consistently call that coupled to other stuff, and now I'm focusing on the physics that would come from phi having additional couplings to some scalars chi, let's say. And there's also a kinetic term for chi, which I neglected to write here. Well, no, good point. It's not really. I'm adding more to the problem. In this one, nobody asked about that because certainly at low energies it boils down to single field inflation. Here, in fact, you guys are. It's great. You guys are asking all the right things. It does make me worry I'm going too slow, but if you don't tell me, if I am, you should tell me. But indeed, you cannot, especially if mu here, let's say, is very small, in an appropriate comparison, you cannot integrate out this chi. It's there. On the other hand, you see from this that as phi rolls through this point where it becomes light and then continues on, each of these sectors gets heavy again. So there is a sense in which the dynamics is effectively single field, but it's affected by the dynamics of these chi's, and there's no way to write an effective Lagrangian for just phi in this problem. That's quite right. So I included the chi's explicitly. Phi I are just points, just a set of points that I put in. It's analogous to phi naught over there. It's just some fixed constant point in field space. This is just a constant in this action, so just constant.
And should we define in such a way that our observable or how?
Well, okay, so there are various ways this can affect the dynamics. Actually, Leonardo and I have a scheme to get back to this toward the end of our lectures with some specific motivations. In an interesting regime of parameter space where these terms come in, and in that context or in any specific enough context, one can answer your question of in this kind of setup, what is, first of all, does it give inflation, and is it viable, and what additional predictions are there? So, well, it'll turn out that this has an interesting sort of non-Gaussian correction, for one thing. It's also true, since you asked, that although I said, I contrasted this with dBi, this has the same feature if these points are closely spaced enough that even on a steep potential, one can have inflation, simply because the field, in this case, the field dumps energy into this sector. So what's going on is, as I was going to unpack in more detail, like in any system with a time-dependent Hamiltonian, here we have a time-dependent frequency for these chi's, and that leads to their production. So there's some particle production. And, that can actually easily be strong enough that it slows the field down on, again, even a steep potential. But there's another range of parameters where it's not that finely spaced, but these effects still come in as sort of periodic effects that contribute to the predictions for the perturbations that we'll get to. So there's a whole range of possibilities, ranging from a novel mechanism for inflation that slows the field down, in this case because of these non-adiabatic effects, it dumps its kinetic energy into this sector. So ranging from that to basically some slow roll scenario where on top of the slow roll there's some additional features. To answer your question, long story short, to answer your question in any detail, we need to agree on where we want to be, and I just haven't gotten to introduce enough to. But another good question. Okay. Well, so I guess it's almost. I guess I'm pretty much out of time. Is that right? Yeah. Okay. So, what I will, I guess, start with next time is, it's kind of okay. What I'll start with next time is just a slightly more about how to treat time-dependent field theory, such as this, partly because that then applies also to the generation of the density perturbations, and then I'll flash the current status of the data as I advertised, and then I'll explain why this turns out to be related quite directly to observable gravitational waves, and then with all these motivations, we'll start into the string theory. So let me stop. Any remaining questions? Yeah.
So you were originally saying that the worry was that heavy degrees of freedom could ruin inflation, and this is an example here you were giving of where it doesn't ruin.
Yeah, exactly. So, yeah, there are a lot of ironies in the subject, of which that is one. So it's both a challenge and an opportunity. I should say another energetically favorable thing that can happen is that the whole thing gets destabilized. That some scalar field runs off, and in some steep potential of its own. And in string theory, we're faced with basically two classes of directions in field space. I'll explain, and ways in which those scalar fields can plausibly get stabilized. Basically, half of which give this behavior very simply, and we'll explain those funny powers I mentioned over there. And then in other directions, basically there are two types of so-called moduli stabilization structures. It's a very trivial thing again. In some directions, you have a metastable potential like that. In others, you have something like this, something like an x plus 1 over x type behavior, for reasons that are quite simple to explain when I get to it. And it's in these directions that this flattening effect works very simply, whereas in these directions, it tends to instead do the other energetically favorable thing, which is to destabilize. But you totally got the right point here, which is that the back reaction on these heavy fields can be a blessing. And again, it's the only reason why certain well-motivated scenarios remain viable. So I think even though it's a trivial thing mathematically, I think it's worth dwelling on. Thanks for the question. So any other? Yeah. That's a bit of a misnomer. It's because when Andrea Linde thought about it, he also thought about the problem of initial conditions, and it was kind of in the context of this model that he considered a scenario with many regions of the universe. Okay, so there's a longer story here, but basically, if you go far, so I said at 15 Planck units, you get your 60 equals. If you go way further, you get into this phase called eternal inflation, where there are regions which are inflating and other at very high scale, and others, at various different scales. Each point exits, but there's always something left inflating. And that kind of picture of the global universe was thought about originally in the context of this model. However, that's incidental to its phenomenology. Yeah, but it's, in fact, the field has started calling this, large field inflation, this whole thing, large field inflation for that reason. But yeah, thanks for the question. Any more?